I don't know, do you guys need, if you need a break, you can leave, come back. I feel like it's a long haul, you're getting restless. Oh yeah, so she's asking a good question. The calendar has in it that President's Day is Monday and we have class off on President's Day, and then we have class on Friday instead, right? And my plan is to do class on that Friday, okay? That said, I may need to either have a substitute or have an online class for that Friday. And the reason is because I also have to be at a conference on that Friday for biology coordinators throughout the state to work on this mass transfer for an agreement amongst all colleges to have things transfer. So the calendar is for class to be on Friday. My other class is canceled, and this class is scheduled to be on Friday. I'm not going to hold class on President's Day when you guys have a scheduled holiday, but I might record a class on Thursday and just have you guys watch it that week. Or record the class on President's Day even, and just have it up for that week and pick up from there on Monday. Is that a preference for you guys? Everybody's nodding their head. Do you like? Yep. Yeah, the logic is because there's so many Monday holidays that we miss Monday classes, and especially if you have like a lab on Monday, then like your class is really messed up. But I also understand that a lot of people plan on having a 4-day-a-week schedule, and Friday is a work day, or Friday's a travel day if you're commuting from somewhere. Or are you guys okay with YouTube videos? Like those, for those of you that are looking at them, they work for you. Do I need to draw on the screen more for you to know what I'm pointing to? I'm terrible with this new smart board. I'm not drawing as much as I should be. I can work on that, especially if it's only a recorded video, making sure that I'm pointing with the marker so you know what I'm talking about. Okay, so we'll go ahead and pick up with chapter 2. And you guys sort of foreshadowed my plan on that Monday is a Friday. I was still figuring out when I was going to report what I was going to do there, but it sounds like you guys would be perfectly happy with a recorded class. Oh yeah, we could totally do that when everybody comes back. It is impartial. I do like to have it be a democracy, and I like to vote as a team what we want. So maybe I'll do that at the end of class. Okay, so we're going to start chapter 2 and talk about chemistry. And I always like to ask, how many of you have had a college level chemistry class before or are in one now? Okay, how many of you feel good about your high school chemistry background? How many of you are generally terrified by chemistry? Okay. I fall in the genuinely terrified of chemistry category, I have to admit. We are going to do just enough chemistry for what you need to know to get through this class. Okay. If you are in chemistry or who have completed college level chemistry courses, you can be like, but, and I'm like, okay, we're stopping here. So there's a lot more to chemistry than what we're covering, for sure. We're keeping it at the surface, and we're jumping ahead. We're going to do kind of like all of the first year of chemistry, hitting the highlights we need for this class in this one chapter. Okay. That being said, this chapter and the next chapter are really foundational to everything else for the rest of the class. If you don't understand what's happening in chapter 2 and in chapter 3, you're going to continue to not understand things for the rest of the semester, because a lot of these things are going to come back around and be important again later, and things from chapter 2 are going to be essential for chapter 3, and so the confusion can build. So I want to just give you the warning that anytime you're uncertain about something here, come to me, go to the peer tutoring center, make sure we fill in the gaps so that as you move forward, you don't have this like weak spot that is making other content hard to learn. Okay. Hopefully some of this is a little bit familiar and hopefully not too scary. So we're going to just do the basic chemistry that is needed to understand life. We're going to start by looking at the elements and atoms, which are the building blocks of molecules. We're going to talk about water, and next week's lab will be pretty much just about water. Because water is very important for life. Life evolved in water, and all of our chemical reactions in biology are assumed to be occurring in a water environment, which changes how we understand our basic chemistry in some ways. So we're going to have that context, and then we'll talk a little bit about carbon, and that conversation about carbon is getting us ready for the next chapter, where we'll look at sort of the chemistry of the body, the chemistry of molecules. Okay. So let's start really basically by making sure that we define what matter is, and then we're going to talk a little bit about matter and elements. So the definition of matter is anything that occupies space and has mass. Okay, and that mass may be something that is so small that you yourself are incapable of measuring it, but that doesn't mean that it doesn't have mass. Okay, the three states of matter, when this is going to be important for our conversations about how biology happens, are solid, liquid, and gas. Okay, so the matter that is in a solid form is very closely packed together. And the fact that that matter is really closely packed together is what gives that a solid feeling, right? If I touch this table, it feels like it's one continuous unit, right? But it's actually made up of billions of tiny little pieces that are packed close together in a solid form. Okay? So solid is all of the matter is compressed into the same place. In a liquid, the matter is a little bit less compressed. It's spaced out a little bit more, and it's moving around in the space that it's given. Okay, liquid flows freely, and it fills the container that it's put in. So if I put this water into this glass, then the liquid is going to take on the shape of the glass. If I pour the glass out onto the floor, the water is going to have no shape because it's just going to spread out a lot across the floor until it runs out, right? Liquids are contained by the container that they're in. They're shaped by the container that they're in. So they're going to have that shape. Gas is the same way. Gas expands until it completely fills the shape that it's in. So if I take a stink bomb and I throw it on the floor right here in front of us, then all of the gas molecules of bad smell are going to expand until they're evenly distributed in this room. Right? Assuming that our airflow is working, it would actually start to leave this room and go out through the whole rest of the building, right? Because the container is whatever space you put it in, and it's going to fill that container. I'm getting beeping in my ear, and I don't know what that means. I'm afraid it means it's running out of battery. So we have solid, liquid, and gas. Okay. We are not going to worry about memorizing the periodic table of elements or knowing the specific properties of most of the elements, but I do want you to know that an element is matter with a specific chemical and physical property, and that it cannot be broken down into a simpler form. So that is the smallest unit that that particular characteristic of chemical and physical properties can be found in. Okay. So all of the elements that are listed here in the periodic table are things that exist out in nature. Most of them are naturally occurring. They're just part of the stuff that makes up the planet. About a dozen or so of them are man-made that only occur because of processes that humans have brought about that has caused them to be made. But all of these individual elements, each one of these boxes represents something that has a specific set of properties. And this is the smallest unit it can be found in. It can't be broken down beyond the element. Okay. We can combine these elements to make something that is bigger, and frequently in combining them, we get something with a new set of properties. So, for example, here we have sodium, and over here we have chlorine. If we add those together, we get NaCl, which is table salt that you would put on your food, right? Sodium over here is a solid metal, and chlorine over here is a toxic gas. Neither of them independently is something you would eat, right? But you put them together and you get tasty, right? They have new properties when they come together. They have their own distinct properties when they're separate, and when we combine them together, they take on new properties. Okay, that was the next one, right? In biology, 25 of these elements are essential for life. So living things cannot survive, or living things don't exist without being made by those 25 elements. Okay. Of those 25, really only 4 of them are dominant. Okay. 96% of the human body is made of just 4 elements: oxygen, carbon, hydrogen, and nitrogen. A bunch of that oxygen and hydrogen are in the form of water, because about 70% of your body by volume are water. Okay. So these 4 elements make up the majority of the human body, and with a little bit of tweaking, that's pretty analogous across most life forms. Okay. These other elements are still necessary, but they're in much, much smaller quantities. Right? If you look at percent of by weight in the human body, these 3 down here, iron, fluorine, and zinc, are trace. Right? They're too little to even really report a measurement on. But at the same time, if you don't have enough iron, you can't efficiently carry oxygen in your blood. Right? If you don't have enough zinc, you can't build things that you need to build in your body. Your body doesn't function. Those things that are found in small amounts but that are essential, we call trace elements, and they are essential in minute quantities. Generally, trace elements are things that are also toxic in large quantities. So you could be poisoned by trace elements if you had too much of them, but they're also essential in some small amount. I already mentioned without iron, you can't transport oxygen. And then iodine deficiency prevents production of thyroid hormones. And the thyroid hormones regulate your metabolism. They help your body decide when to burn nutrients and when to store nutrients, and to make sure that you have enough energy to function. Okay? If you're not getting enough thyroid hormone, you don't use energy from your food, and you end up being unable to function. People who have thyroid deficiencies are constantly exhausted. They just want to sleep all the time. Can't function. Thyroid deficiency can also lead to the production of goiters, and so this individual here has a very large swelling in their neck. That is their thyroid gland swollen out of control by an iodine deficiency. This is not an uncommon thing in human populations for us to be iodine deficient, because we don't eat enough of the things that naturally have iodine in them, like sea vegetables, kelp and algae, those kinds of things. So our solution has been for a very long time to iodize salt. And so many of the salts that you would buy have actually had iodine added to them in small trace quantities. You put a little bit of it on your food, and you just, in the background, make sure you get enough iodine. Okay, so all of those elements that we looked up, or that we looked at really briefly on the periodic table, and all matter is composed of atoms. And the atom is sort of that smallest structure that has all of the properties of the element. Okay. The atom itself is made up of subparticles, and we're going to go through and look at all of those in detail. And so I want to make sure that you know what an atom is and what it's made of. So an atom is sort of the smallest indivisible unit of an element, and it is made up of 3 particles: the electrons, the protons, and the neutrons. Okay. Electrons have a negative charge and a negligible mass. They're tiny, 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 tiny. We really can't fully grasp how tiny they are. They are almost impossible to measure in any meaningful way. So they're very, very, very small, and they have a negative charge, and they tend to be found on the outer edge of the atom. We'll come back to that. Protons have a positive charge, so they're opposite of our electrons, right? And they have a mass that is measured as 1 atomic mass unit. Okay. I don't need you to know what an atomic mass unit is. It's down here. It's 1 Dalton, 1.7 times 10 to the negative 24 grams. That's just to give you an idea. Put 24 zeros in front of this. It's very small, right? But the reason that I mentioned 1 AMU is because a proton is the same size as a neutron, which is also 1 AMU. So these two particles are of measurable size. They're still infinitesimally small to our eyes, but they can be measured. They are considerably larger than the electrons. Okay. The protons and the neutrons are both found in the center of the atom. And they, just like we talked about the nucleus of the cell, the atom also has a nucleus. It's the center structure. Okay? And that is going to be made up of a congregation of the protons and the neutrons of the atom. So those two things collectively together make up the nucleus. Okay? Protons are 1 AMU, neutrons are 1 AMU, so they're the same size. Protons have a positive charge, and neutrons are neutral. They have no charge. And so you can remember their charges because proton, the P goes with positive, and neutron is neutral or no charge. And so you can match those words together. Right? So in the center of the atom, we have the nucleus. The nucleus is made up of protons and neutrons. And then outside of that nucleus, we have the electrons. Okay. You guys are all with me so far? This is familiar, right? Okay. Oops. Keep skipping multiple cells. All right. So I already said that the atomic nucleus is the center of the atom and contains the protons and the neutrons. The smallest atom, an atom of hydrogen, has one single proton in its nucleus. That's the entirety of the nucleus. There are no neutrons, and there's only one proton. So that's our very smallest atom. Our next smallest atom has 2 protons and 2 neutrons. So it has 4 same size structures inside of it. Right? So this has a larger overall mass, it's bigger than this, right? But they're still both very small atoms in the grand scheme of things. Hydrogen is here, helium is here, they're the 2 smallest. Okay. All right. Now, have I talked to you guys about my slides, bold versus underlined versus italicized? I mentioned that before, right? So words that are bolded, like the atomic nucleus, are words I could test you on, would expect you to know on a homework or quiz or an exam. Those things that are italicized or underlined are words that you might hear them again, but they're not things I would ask you to define or describe on an exam, right? So the mass number and atomic mass are useful to know, but I'm not going to test you on them. So the mass number is just the number of protons plus the number of neutrons. So you add those up together and you get the mass number. So here our helium atom has 2 protons and 2 neutrons, so its mass number is 4. Carbon has 6 protons and 6 neutrons, its mass number is 12. Okay, it's just how many individual units are inside the nucleus, basically. The atomic mass is the actual mass of the nucleus. Okay? It's approximately equal to the mass number, but it's usually not the same. Okay? And the reason is because some individual atoms have an exception and have a slightly different sized nucleus. Okay? So this is sort of the average mass number of that particular element. This is the actual count for the atom you have in front of you. Okay. The atomic number defines the proton. The number of protons that are in that particular atom define what element it is. Hydrogen has 1 proton. Helium has 2 protons. Carbon has 6 protons. That's universally true. It's how we know that it's an atom of carbon or an atom of helium or an atom of hydrogen. Okay? The number of protons inside that atom define it. Okay? Typically, the number of protons also equals the number of electrons, and so our atom has a neutral charge because the positive elements balance out the negative elements. That's not always true. We'll look at exceptions, but in the grand scheme of things, this is often true. So here we have helium again. Helium has 2 protons in its nucleus, so its atomic number is 2. It also has 2 neutrons, so its mass number is 4, and then it has 2 electrons. And we can either show those electrons as individual structures out here outside of the nucleus, or we just show a cloud around the nucleus, and we say that there are 2 electrons there. Okay. I'm going to stop here. We'll take a little break. Those of you that need to leave or want to watch this later are free to leave. I'm going to plug in this headset. I'll post it on Moodle. And I will go ahead and